In the last lecture, we defined the geometric configuration factor, that is f A1 to A2. This tells you the fraction of radiation that leaves surface A1 and reaches surface A2. So, the term geometric configuration factor is the correct definition, because this depends on the geometry of the problem, the various geometries involved and the relative configuration of the two surfaces. But since this term is long and unwieldy, people use shorter terms like shape factor or view factor. So, these are words normally used to indicate this term, which is geometric configuration factor. We saw that this can be calculated by the direct integration of the equation over both the areas, but this can sometimes get quite complicated and not easy to evaluate. So, it is useful to know for practical application some shortcuts and other techniques to evaluate this for a given situation. So, we start with one example in the last lecture, which is for situations where one dimension is very large. So, when one dimension is very large, the problem is essentially two dimensional, but in radiation, even in a two dimensional problem, you have to integrate over third dimension. But if the third dimension is very large, you can appeal to law of conservation of energy to simplify the problem to some extent. In the last class, we saw that if you have a triangular enclosure, which is infinite in the third dimension, then you can easily calculate the shape factor between 1 and 2 and 1 and 3 and 2 and 3 by just using the law of conservation of energy and also the law of reciprocity. So, in the last class we derived this equation using both the law of conservation of energy and and we saw that f A1 A2 was equal to, suppose we draw the triangular enclosure here. We saw that we can derive an expression for f A1 A2, that is between 1 and 2, in terms of the area of A1 plus area of A2 minus area of A3 divided by 2 A1. So, if you recall, we derived this just by looking at the 6 shape factors involved, F12, F21, F13, F31 and F23, F32, and we had 6 equations, 3 equations for the satisfying the first the law of conservation of energy for the 3 surfaces, and then 3 equations that involves reciprocity. So, we could solve for all the shape factors, and so we got this result. Now, this result can be made to look simpler, because all the dimensions of this enclosure are infinite into the page. So, we can replace all the areas with lengths. So, length of 1 plus length of 2 minus length of 3 by length of 1, where L1 is this length, L2 is this length, and L3 is this length. So, you just have to measure the lengths of these 3 sides of the triangle and you will get the shape factor. So, this is a very convenient and simple method to calculate shape factors without actually integrating those equations. Although it is a nice result, you might wonder how many real life situations will you encounter which has triangles with straight sides like these. There are not too many. Okay. The real world is more complicated. It has curved surfaces, and it may not actually, for example, suppose you want to find shape factor between these two surfaces 1 and 2. This is not two straight objects, and there are, I do not see any simple triangular enclosure. But what was shown by Professor Hottel from MIT was that even if the real problem does not have straight surfaces, suppose there was concave surfaces, if you recall, the result obtained here was valid only for non-concave surfaces. That is, those for which f A1 A1, f A2 A2 and f A3 A3 were equal to 0. But in many real life situations, you are going to encounter surfaces which are concave, that is, which see themselves, and in which case f A1 A1 will not be equal to 0. So, how do you deal with such situations? So, for such situation we need to extend what we had obtained just now for triangular enclosure to a more general case. Okay. So, let me derive a more general technique available. So, let us say this surface 1 and this surface 2, and both surfaces have concave features. So, that f A1 A1 is not equal to 0, and so is the case with A2 A2. So, how do we tackle this problem? And if you are unlucky, there could be other surfaces intruding into this space and making our life somewhat more difficult. So, the solution suggested by Professor Hottel of MIT was to create two triangular enclosure within this one. How do you do that? So, let us take the edge of this surface, let us say that is A, the other edge let us say is D, and let us say the edge here is C and the edge here is F. Okay. So, what we need to do is now create artificial surfaces which are not concave. So, one example I am going to do is I am going to take the edge of this protrusion, draw a straight line this way and draw another straight line. So, A, B, C. So, A, B, C is non-concave because it is made up of two straight lines which are tangent to this point B. So, this is not concave. Similarly, you choose the extreme point E here and draw a tangent which join that, and draw another tangent which joins F. So, this is also, although it does not look like concave, let us draw a little better. So, this is also, so similarly this is E, remember that. Similarly, DEF is also a non-concave virtual surface. Okay. Now, both the surfaces have concave portions. So, now we will draw an imaginary surface now AGD, which is always convex. Similarly, here also we will draw another imaginary surface CHF. So, notice that AGD is also non-concave and CHF is also non-concave. So, now we have created a rectangular enclosure with non-concave surfaces. That is, surfaces wherein the self-weaving factor, that is F A1 A1 or F A2 A2 or F A, they are all zeros, because these surfaces do not have concave features. Of course, ultimately we have to find F12. Okay. So, our aim is to find F12 given the geometry. So, what you are going to do is we are going to construct two more surfaces. One is joining A and F straight, and this was C and D. Both these are straight lines. So, what we have done essentially is constructed two triangles out of this rectangle. One is ABC D, ABC ABC, let us say ABC CHFA. Okay, that is one triangle. And the other triangle is AF H. So, the two triangles we have constructed would be such that they will have a common base. So, you construct two triangles with a common base and you calculate the shear factor using the formula for a triangle. Okay. So, that is the purpose here. So, now we will calculate from AGD. So, with AGD as the base here, we will calculate for the triangle AGD ABC, this triangle. So, let me go to next page. So, consider triangle AGD CBA. So, for the triangle, from the formula for a triangle, you can write F AGD to ABC, both are concave surfaces, and according to the triangle law we derived, this will be equal to length of AGD plus length of ABC minus length of CD divided by twice the length of AGD. This is by applying the triangle formula for non-concave surfaces. The triangle is AGDCBA. Similarly, consider the triangle the same base, that is AGD FA. Okay. So, based on this you can say F AGD to DEF is equal to length of AGD to length of DEF minus length of AF divided by twice length of AGD. So, we have taken two triangles with a common base. For each of these triangles which contain by construction non-concave surfaces, we apply the formula for a triangle enclosure with non-concave surfaces and arrive at the result. Now, why this is so useful? Because now we can write down by applying the first law that F AGD to F CHF is equal to 1 minus F AGD to ABC minus F AGD to DEF. So, what we have done is we have first calculated the shape factor from surface AGD to the two side surfaces, and once we have done that, you have taken from AGD to ABC, AGD to DEF. So, the remaining unknown is AGD to CHF, which is what we need, but we know that the sum of shape factors AGD to ABC, AGD to DEF and CHF is equal to 1, and hence knowing these two we can get the third, because the sum of the three is equal to 1. So, that is what we have used here. So, this is now remember we have still not reached the end of our derivation, because we need F12. Okay. So, how do we get now F12? That is the issue at hand. We have managed to get F AHD to CHF. So, let me again remind you what we have managed to get, F AG to CHF. Now, we want to get F12. So, we have to take two more steps. So, we will now write F AGD to CHF as equal to F AGD to 2, because whatever radiation, let us go back to the, whatever radiation leaves AGD and reaches CHF also has to reach 2. Once it crosses CHF, there is no other place to go except surface 2, and these constructions are done to aid our derivation. Remember that all these are what are called as taut strings. That is why the method we are now deriving is called the Hottel's cross string method. We are drawing two cross strings here and two parallel strings here, and all these strings are so drawn that the triangle that emerges from this construction is a triangle containing non-concave surfaces, and hence the self viewing factor is 0. So, we can apply the triangle formula to get the result in terms of the length of these strings, and so the final step here to calculate F AGD to CHF which is still is equal to 1 minus we got f AGD to ABC minus f AGD to DEF by twice the length of AGD. Okay. The story is still not over, we want F12. Now, the way we are going to get F12 is use reciprocity, which says that length of AGD f AGD to 2 is equal to length of 2 to f 2 to AGD. This is the reciprocity. It is always valid between any two surfaces, the reciprocity is always valid. Now, when you calculate f 2 to AGD, whichever radiation reaches AGD from 2 has to reach 1. Once it crosses this imaginary surface, it has to reach 1. So, therefore, we have reached our final goal is L2 F21. Okay. So, we will write F21 is equal to L AGD by L2 F AGD 2. Now, F AGD 2 is given there. So, you can write these. So, finally, the final answer for F21. Now, note that when you substitute here, the L AGD will cancel out. So, 1 minus F AGD ABC AGD DEF by 2 L2. So, when I say L2, I mean the actual length you have to measure along this crooked surface, that is L2, not the length of the string which we have drawn above that, that is CHF, the actual length of the surface 2. Now, we can substitute expression for AGD and AGDDF here, and final expression you will get for F21 will be length of AF plus length of CD minus length of ABC minus length of DF by twice the length of the surface 2. Now, the best way to remember the result is that it is the sum of crossed strings minus sum of parallel strings divided by 2L2. So, this is a very simple and clean result, and the only challenge is for you to correctly identify the cross strings and the parallel strings to be drawn between two surfaces. And in drawing these strings, you must take special care to ensure that you create two triangular enclosures, each of them having only non-concave surfaces. So, that you can apply the law that we obtained for non-concave triangular enclosures. So, to understand how to apply this, what is known as the Hotel's cross string method, we need examples. Unless you try this out for various practical examples, you may make a few mistakes in drawing these strings correctly. Okay. So, I am now going to give a series of examples to show how to apply the Hortel's cross string method to a number of practical situations. And you should also now try out this with few more examples to ensure that you are able to get results without any make any serious error. Okay, let us take one example is similar to what we had done in the last lecture. Suppose you have two parallel plates of length L and distance d, and this is 1 and this is 2, and you want to calculate, let us say f21, okay, and the edge of this let us say is AB and CD. And if you follow the spirit of the cross string method, you can see that you must draw two parallel strings and then two cross strings. Okay. And the Hortel's cross string method says that F221 will be equal to sum of the cross string, that is AD plus BC, minus sum of the parallel string, that is AC plus BD, divided by twice length of surface 2. Now, this example was very simple because the basic surfaces are flat and easy to visualize what the strings are. So, final result of this would be AD you know is L squared plus D squared square root plus BC is another L squared plus D squared, it is all symmetric here, 2 minus AC and BD are both D's. So, the final answer is a nice and simple answer. Once you get an answer like this, it is important to check whether your results make sense. So, it is good to look at asymptotic limits. What are the asymptotic limits? One is L is much greater than D. The length L is much larger than D, all of you can see that as the gap between the two plates becomes smaller and smaller, not much of the radiation will escape through the sides, and hence the shape factor F21 must tend to 1. And you can see it here, if you neglect D compared to L and again neglect this, F21 will tend to 1. That is fairly easy result. And so, that is a result you will usually remember. And the other limit is, if L is very small compared to D, D is very large, the two plates are very far apart, then the chances of radiation from one plate ever reaching the other plate is very low, and in the asymptotic limit this value will tend to 0. Okay. And both these are easily seen in this result. If you neglect L compared to D, D minus D is 0, you get 0. So, in the other case we neglect D compared to L and we got 1. So, both limits are satisfied. So, we are quite sure that this derivation was right and we did get the right answer. This of course was a simple problem involving very simple geometries. Now, let us try something little more complicated, so that we get familiar with the application of these laws. Okay. Now, so I am going to take a few more examples in which we can apply the cross-checking method. Now, the example which will test your ability is the example where there are obstructions, where things come between the two surfaces, so that your ability to draw the parallel cross strings becomes an issue. So, I am going to take one example wherein this issue becomes very important, and this example is somewhat complicated, and so let me show the example and argue how you would tackle it. Okay. So, let us extend the previous example. Suppose we have two surfaces and an obstruction coming here. So, this is 2, this is 1 and this surface 3. So, this obstruction reduces the view of 1 from 2 and vice versa. How do you apply the cross-checking method? You draw the parallel strings like this. Okay. Other parallel strings of course is as same as before, and the cross strings are drawn like this and like this. Now, we have constructed two triangular enclosures with a common base. So, let us call this edge 4, okay. Let us call this A, B, C, D. So, you can clearly see that F 1 to 2 will involve adding the two cross strings, which are very easy, no problem, minus two parallel strings, which is this is our length, you are talking length of BC, then length of A4C minus length of plus length of BD divided by 2 length of 1. So, do it properly. So, length of AD plus length of BC, that is the cross string minus parallel string. So, in this problem, when an obstruction appeared from this side, we have to draw the parallel strings in such a way as to ensure that the obstruction was kept out. As a matter of fact, there is a simple thumb rule to decide whether you have drawn the parallel strings and the crossing correctly. If you have drawn all the strings both parallel and cross correctly, then the parallel strings will be so drawn that any radiation leaving 1 reaching 2 will not cross the parallel strings. That is, any ray which leaves 1 and arrives at 2 should not cross the parallel strings, and any ray which leaves 1 and arrives at 2 must cross the cross strings. So, after drawing your parallel string and cross string, draw a few rays, extreme ones especially, to see whether the strings you have drawn are such that the parallel strings do not allow radiation which should reach to leak through the parallel string, and the cross strings are such that every ray which leaves 1 arrives at 2 does cross both cross strings. Once you are guaranteed that, you are ensured that the answer is okay. So, this is an example which is little more complicated than the rest. Now, let me take a few more examples to illustrate this point of view, a little more complicated one, so that you understand the logic of this. Now, let us take a little more involved example, the same logic as before. Now, you have two obstructions. Okay. The surface 1, surface 2, there are 2 obstructions here. So, how do you draw the string? So, you have to of course draw the one parallel string same as before to keep the obstruction out. Then you have to draw the cross string here like this and like this, and this one parallel string, the other parallel string goes like this, goes over this obstruction and goes back like this, and one cross string goes like that and the other cross goes like this. Okay. So, this is a little more complicated than the other example, but still you can draw various rays like this one to make sure that this ray, which is a part of a parallel string, is a ray which does not reach 2, and hence that is okay. And so, you can do some construct and see that, for example, here this ray from 1 can lead through this, but that is not a ray which will reach 2. So, that you have to guarantee that does not reach 2. So, then you can calculate the length of these 2 strings and get the answer. So, you can see that as the problem gets more and more complicated with obstructions coming in, you got to be a little careful about how you construct your strings and do a few trial checks to ensure that your triangles are drawn properly. Now, let me just take one more example to complete our discussion, so that there is sufficient. So, there are 2 obstructions here, one here and one here like this, and one here like this. So, you can see correctly this should be one parallel string, that is very obvious. The second parallel string has to keep out this obstruction. So, you draw it like that, draw over this and then over this. So, that is very easy. In this case, crossing is very easy, this one and this one. So, you can see that you have drawn your cross and parallel strings such that you have ensured that the ray which crosses the parallel string never reaches the other surface. The one which crosses both cross strings must reach the other surface. So, you can draw various rays and make sure that you have ensured that the construction of the cross and parallel strings is accurate, and that satisfy the rule that any ray leaving surface 1 and reaching surface 2 must cross both the cross strings, and any ray leaving 1 and not reaching 2 must go through the parallel string. So, this is satisfied here, and that should be sufficient to ensure. Now, let us take one more example here, the simpler one. We go to now not just flat geometry, but circular geometry. Here is a circle, here is a flat, both are infinite into the page. So, you do surface 1 and surface 2. So, first is you draw a tangent, and then you draw one right along this, and then where you can draw a tangent to this. Okay. So, this should actually be in dotted lines. Similarly, you draw this until it touches the tangent and then go like this. Okay. So, you can see that the 2 parallel strings, this one and this one, are just straight lines, no problem. But the cross strings involve a curved portion and a straight portion. So, what you have done really is that you have again constructed two triangles. Let us call this A, B, C and D. You have considered one triangle A, C, B, A. So, this triangle is a triangle consists of non-concave surfaces. So, you can apply the triangle rule. And the surface A, I will call this tangent as E, AED B, A, AED B A, another triangle consisting of again non-concave surfaces with a common base AB. So, I can apply the same rule that we have applied to derive the Hortel's cross string method, and you will get the answer that it is the sum of the two cross strings minus sum of the two parallel strings by twice the length of AB. So, only the calculation is a little messy here because it is a circular object, but otherwise the results drawing the string is fairly straightforward. Now, there are situations where you may not even have to draw the strings directly. For example, suppose there is a circular tube and hollow tube and a solid tube here. Okay. This surface 2 and this surface 1. Okay. And you want to find F A2. Now, what is the difficulty here? Because the problem is fairly somewhat involved. So, the best way to do this problem is to construct now an imaginary surface So, I want to notice that this surface A tangent to B, curved surface D and tangent to D, ABCD. ABCD is a convex surface. Okay. Because it is a convex surface, F ABCD to ABCD is 0. It cannot see itself because it is convex. The only surface ABCD can see is 2. Therefore, F ABCD to 2 is equal to 1, because radiation leaving ABCD cannot see itself, it does not see any other surface except 2. So, all the radiation leaving ABCD has to reach 2. So, this is a construct for a convex surface. Now, given that, applying reciprocity, assuming this infinity into the page, length of ABCD into F ABCD to 2 is equal to length of 2 into F of 2 to ABCD, right. This is applying reciprocity. So, since you know the length of ABCD, since you know F ABCD equal to 1, so you can obtain the fact that F 2 to ABCD is equal to 1 minus length of ABCD divided by length of 2. But you wanted F 2 to F A 2 to A 2, okay. And that comes out easily, because we know that F 2 to ABCD plus F 2 to 2 is equal to 1. By applying the law of conservation energy, any radiation leaving 2 has to come back to itself or go to ABCD. Now, since we know what is the value of F 2 to ABCD from this equation, we substitute the finally we get F 2 to I am sorry, I made correction here, let me just make correction here. This is nothing but F 2 to ABCD is L ABCD by L 2 only. Now, I substitute that here, now we get 1 minus L ABCD by L 2. Okay. So, this is just L ABCD 2 by reciprocity. Then you apply this rule here and you get the final answer, that you just have to calculate the length of ABCD and length of 2, take the ratio and 1 minus that is the answer. So, here we are not directly applied the Hotel's crossing method, but the spirit has been used, which is that a convex surface cannot see itself, and if a convex surface is bounded completely by another surface, then all the radiation leaving the convex surface has to reach itself. So, let me give a few more examples to highlight that part, very simple examples. Suppose there are two concentric circles or spheres. This is surface 1 with area A1 and surface 2 with area A2. Okay, straight away see that F A1 to A2 is equal to 1, because 1 cannot see any other surface, and from reciprocity F A2 A1 is equal to A1 by A2, and therefore, F A2 A2 is 1 minus A1 by A2. So, these kinds of simple calculation involving reciprocity, common sense, other thing is called configuration So, we call them configuration factor algebra. So, this is essentially using common sense, arguments from symmetry, reciprocity and the first law of thermodynamics. So, these all can be very useful for you to generate expression for shape factors without actually doing the integration of the equations. Okay, let us take a few more examples of this kind of situation, where without integration you use your understanding of the symmetry of the problem to get the answer. Let me give one example here. Let us say, suppose you want to calculate from a sphere to a disk. Okay, what is the shape factor? Sphere is 1, disk is 2, and you are given this length is L, and this radius, let us say, is R2 and this radius is R1. Okay. Now, this problem is 3 dimensional, and hence you cannot use the ideas of the Hodel crossing method here. It is a 3D problem, but you can appeal to symmetry. If you take this distance, which is nothing but L squared plus R2 squared, and draw let me draw it in a simple way. You draw an imaginary sphere. You can see by the symmetry of the problem that radius leaving 1 and reaching this surface 2, f a1 to, and this is let me just call this surface 2 and this surface as 3, this. So, this is a disk, this is a cap. Okay. So, what we are going to say is that if you draw this imaginary sphere, then f a1 to a3 is nothing but area of the cap by 4 pi L square plus R2 square. Okay. And the area of the cap can be obtained, this cap can easily be obtained by from books, geometry book, no problem. So, what we have done here is we are not we have just exploited the fact that you can draw a imaginary sphere around this sphere which encloses this disk. So, the argument is that f a1 to a2 has to be equal to f a1 to e3. This is common sense that any radiation which leaves 1 and crosses 2 has to also reach 3. Okay, that is the only idea that is being exploited here. And so, we are able to derive an expression for f a1 to a2 without actually integrating any equation, by just appealing to the symmetry. The problem has a symmetry which exploits this fact, but I must warn you, sometimes symmetry can mislead you. Here is an example in which you think of a cylinder here and think of various other cylinders around it. And F1, let us say I want to calculate F1 2. So, there are 6 cylinders placed symmetrically around central cylinder. Now, one may be tempted, and they are placed equally spaced here. One may be tempted to conclude that f 1 by 2 is equal to 1 by 12, but this is not true. Because you might mentally construct imaginary cylinders, 6 of them, and you may think that the problem is symmetric. There are 12 cylinders, and so each cylinder should get 1/12 of the radiation. But you got to be little careful here, you have to actually construct this and ensure that there is no chance that some of the ray which is going from 1 to 2 is obstructed by, let us say, cylinder 8. If that happens, then f 1 by 2 will be less than 1 by 12. So, one has to be careful. Symmetry is a very powerful concept in this subject, but sometimes you may get a misleading impression of a symmetric situation, but in reality, because of the intrusion from other objects, the symmetry may not be strictly valid. So, one has to be a little careful, but as long as you are alert to the various rays which are traveling in different directions, and you ensure that you do not miss out on the possible obstruction by some of the objects in between, you can do it. Let me just complete this lecture by giving one more example, just to ensure that you are Let me take an example like this. This surface 1 and this surface 2, and everything infinity to the page. So, you can easily draw one parallel string here. These two things are very easy to apply. Then comes the cross string. So, one cross string is very easy, this one. The other cross string you have to apply rather carefully, and the other cross string really has to be like this. Okay. So, these are the two parallel strings, and you can convince yourself that any radiation leaving one not reaching 2 has to go through the parallel strings. On the other hand, any radiation which leaves one and reaches 2 does cross the cross string at one of these points. So, you have to do a few more examples on your own to ensure that you are completely comfortable with drawing these things. For example, this example can best be thought as two plates like this, and you mentally rotate this surface in this direction to get that result. Okay. So, that is what this demands. So, so you saw in this class that a combination of triangular enclosure results and symmetry and first law reciprocity all helps you to obtain shape factors for various simple geometries, but in case it is not possible, of course, you have to resort to actual integration. But today there are lots of data available both in many books on radiation transfer, as well as you can search the internet for data on shape factors.